Welcome to Receding Horizons, a podcast for exploring topics in astronomy and space science. Since antiquity, humans have gazed at the night sky, attempting to decipher its mysteries and find our place within it. As astronomer Edwin Hubble once remarked, the history of astronomy is a history of receding horizons. Our podcast will attempt to answer some of the biggest questions from the oldest of sciences. The mission of this podcast is to explore topics of astronomy and space exploration and share them with the community of Brownsville, Texas. Our valley is entering into the next phase of human space exploration and participating in the era of multi-messenger astronomy. We are providing a forum of discussion among people of all ages and expertise to bring awareness about our role in this next exciting era. These are Receding Horizons.
Somewhere in the universe, two black holes collide. As heavy as stars, as small as cities, literally black holes. Tethered by gravity in their final seconds together, the black holes course through thousands of revolutions about their eventual point of contact, churning up space and time until they crash and merge into one bigger black hole, an event more powerful than any since the origin of the universe, outputting more than 1 trillion times the power of 1 billion suns. The black holes collide in complete darkness. None of the energy exploding from the collision comes out as light. No telescope will ever see the event. That profusion of energy emanates from the coalescing holes in a purely gravitational form, as waves in the shape of space-time, as gravitational waves. An astronaut floating nearby would see nothing, but the space she occupied would ring, deforming her, squeezing, then stretching. If close enough, her auditory mechanism could vibrate in response. She would hear the wave. In empty darkness, she could hear space-time ring, barring death by a black hole. Gravitational waves are like sounds without a material medium. When black holes collide, they make a sound. That was chapter 1, When Black Holes Collide, from Janna Levin's 2016 book, Black Hole Blues and Other Songs from Outer Space. This is Receding Horizons, episode 2, with your co-hosts, Victor de los Santos and myself, Richard Camuccio. And today we're going to be talking about gravitational waves with our good friend, Brina Martinez. Brina Martinez
and black holes.
And black holes, especially black holes, which are the coolest things, I think, in the universe. Brina Martinez is an undergraduate studying physics and computer science at the University of Texas, Rio Grande Valley. She is currently a research assistant at the Center for Gravitational Wave Astronomy and in the Time Domain Astronomy Group operating the Cristina Torres Memorial Observatory, both under the mentorship of Dr. Díaz. Brina is a published scientist. Her research focuses on characterizing noise sources intrinsic to the Laser Interferometer Gravitational Wave Observatory, or LIGO. She has participated in a research experience for undergraduates at Louisiana State University under Dr. Guillermo Valdes and Dr. Gabriela González, and was a LIGO undergraduate fellow at Caltech under Dr. Derek Davis. Brina is a board member and resident astrophysicist at the South Texas Astronomical Society, as well as a board member and secretary at the Brownsville Chapter of the Society of Physics Students. She was the recipient of several awards, including a scholarship from the Society for Advancement of Chicanos, Hispanics, and Native Americans in Science, and a Victor M. Blanco Fellowship from the LIGO Lab and National Society of Hispanic Physicists. She is a gifted public speaker, and I've had the privilege to work with her and make a lot of memories during my time in Brownsville. Brina, welcome to the podcast.
I am glad to be here.
We can have a whole episode just on her credentials.
I was about to say, I need to go into some of that at some point and ask, especially about your work at LIGO. But yeah, that was definitely, it was all needed to be said because from my time in Brownsville, I have to say getting to know Brina and working with her, she's been a big inspiration to me. Right before we started this podcast, she was telling us about her daily schedule and I'm like, I thought I was busy, but...
She just told us about the meetings. There's still all the work that has to go in for
Right.
all of that.
Yeah, just for everybody. She said her free time is after midnight. So Brina, how did you? I want to just start where I start usually with everybody on the show, which is how did you get to where you are right now? How did you get to do all of that stuff I just read, and work at LIGO and at Louisiana State University and work with a professor at Caltech? How did you get into physics? What sparked your inspiration?
Yeah, so I actually talked about this with Victor like a few days ago for another video, but I told him like I didn't actually think I would be a scientist growing up. It was funny because so sophomore year in high school, I was taking chemistry, and I was good at it. Like I'm good at science and I'm good at math, but I absolutely hated it. I hated like doing the work. And my teacher was like, "Oh, why don't you become a physicist?" Like very like ironically, like she's like, "You should become a physicist. Like I think you'd be really good at that." And I was like, "What is that? Like I don't even know what physics is." And then junior year comes and we have to take physics as a junior in high school. And I'm sorry. And I had this amazing teacher. She was like a female teacher that I had for physics. There was other teachers, but she was the only female teacher, and she actually did work with NASA. I found out later on when I took her. And that class was so fun. It was the first class that wasn't boring for me. Most classes were pretty boring because, the material was kind of easy, or like it wasn't interesting for me. And that one was so amazing because you get these equations and these formulas, and you see like how they beautifully interact to create these solutions or tell you how things work and why things work. So that was kind of the start of like, oh, maybe I should become a physicist and pursue this. And then towards the end of the course, we covered a bit of black holes, and that was it. Like I went home that day and did research, like the first time in my life, did research on my laptop and looked so many things up. And since then I went to college and studied physics and ended up doing computer science also, but that was later on. And around my sophomore year again in college, I ended up meeting a fellow colleague, Wendy Mendoza, and Moises Castillo, yes, right? And they invited me to a seminar for the Time Domain Astronomy Group, and Wendy was doing a presentation on asteroids, and I was like, man, this is really cool. I never studied astronomy before. I'm like, oh, this is kind of what we talked about in high school, but I didn't really get to dive too deep into it. And I asked Dr. Díaz if I could join the group, and he was kind enough to say, yes, like come to the next meeting so you can kind of get a feel of what we were about. And I ended up joining the group around October of 2018, and I met Richard and a few other people. They were really nice to me, and since then I did like volunteer work at CTMO. And then the January following that year, I attended a conference for undergraduate women in physics, and I met Dr. Gabriela González after Dr. Díaz told me to go say hi to an ex-student of his. And I was like, okay, I'll say hi to this student. I don't know who she is, but I guess. And then at the meeting, I saw her shirt and it said LIGO, and I was like, what is LIGO? Like, I don't know what this is. And then she ended up giving a presentation, and again, my mind was blown. So then I remember exactly after her presentation, I texted Richard and asked for a bunch of materials on interferometers, and I guess that's where I started. And then a few weeks later, I talked to Dr. Díaz about my experience at the conference, and he told me, okay, do you want to go to Louisiana State University and do research? Out of the blue, and I was like,
Yep.
Sure, let's do this. So I went that following summer, and then after that, I applied for other internships and managed to land a position at Caltech the following year and worked with them. And then it's just been nonstop since then. I started working with stars, and then doing other outreach activities on top of research and studies. And now this coming May, I'll be graduating with my bachelor's.
That's an amazing story. I wanted to ask, like, what do you think, I guess, junior high school Brina would say if you went back and said, oh, you're going to be working on an instrument that's looking for black holes? I mean, talk
With a
about
laser.
with a laser.
I probably wouldn't believe it, because I still don't believe it. Like, who gave me this opportunity? Like, why would they give this to me? I probably, like, I'm like the worst person to give it to. Like, I could break an instrument like in 20 seconds, but they trusted me enough.
They trusted you enough, and you also, now you're a published scientist, and so you've taken this amazing journey only in these last few years, and you're just getting warmed up. That's what's been so inspiring to me. Like, I was in Brownsville for just under 4 years, and in that time I've seen so much growth in your journey. Like, it's incredible. So, and I remember when you asked me for those notes, I think, did I give you the notes from Les Ouches? Did I ever give you those? Or I forget what I actually.
Yeah, you gave me some handwritten notes from when you went to school over there, and I forgot where it was, but
it was Les Ouches, France. Yeah.
Okay. Yeah, you gave me some of those, and I still have those scanned, like, in my iPad. And then you also sent me the courses on YouTube.
Oh yeah.
Like, they were recorded, so like I had watched those. And then after that, Dr. Díaz also gave me a book on the fundamentals of like interferometer, gravitational wave detectors. And I still have his book. I need to return it.
And that book's by Peter Salson, right? Or is that a different? Okay, that's the book.
It was kind of crazy because, so I worked with Dr. Derek Davis at Caltech this past year in 2020, and his mentor for I think it was, I can't remember if it was undergrad or graduate, but it was actually Peter Salson.
That's amazing.
So like it all connected, and I was like,
I have to say, just because we're talking about that, like when I was in France, I was sitting next to Peter Salson. I didn't know who that was at the time, and then it was like the next lecture was being given by Peter Salson, and he stands up and he walks down. I was like, whoa, okay, I was just sitting next to him. So that's
that's one thing that's so cool to me, just how accessible these scientists are. I haven't experienced it, I mean, too much, but even then, Brina, I didn't know that it was that you had joined the group in October 2018. That was only a few months before I also kind of joined the group and started showing up to the seminars. So was it that same lecture that did Dr. González go a few times? Or because I was there in that room in the old building where she did that presentation. Was that the same one, or did she go a couple times that year?
I would say it's the same one, because I remember it was before I left to Livingston, because you had walked in to Dr. Díaz's office. Richard was there, Maki was there, I think Tanya, our friend Tanya was there, and Carol was there, and you brought up LIGO in your conversation, and I think I don't know who it was, said, oh yeah, she's going to LIGO like this summer. Like, we were all there, and I remember it.
This. I remember this too, because that same lecture, I think it's the same one. It's recorded on YouTube on the CTMO page. So like that lecture's there. So everybody who's listening, that lecture is like a lot of historical stuff in our group happened on that day, in that moment. And
yeah,
it's not a coincidence.
Amazing.
It's not a coincidence that Gabriela González was in the room too, because she's so super inspirational. So.
That's amazing, because I knew that story about you, but for some reason, until when you said that date was when I put that together. I didn't know that it was lined up that much. Wow. You did all that just in the same time that we kind of started with stars. That's almost like, fast. Damn, what have I done?
I know, I say the same thing. I mean, like, I'd see Brina studying with Tanya and Victor in the conference room in Calvary. So this is on the old physics building in Brownsville campus. And yeah, like I just remember seeing down the hall, you guys were always in there studying and working on your problems together, suffering together. You know, misery loves company. So
yeah, that was like my second home.
Yeah.
The Calvary days. That's awesome.
The Calvary days. Yeah. Oh, I miss that building. But Okay, so here's an important question, because we've mentioned this a few times. I mentioned it in your bio, and you mentioned it a bunch of times too. What is LIGO? What is it? What is it? I mean, what does it stand for? What does it do? And maybe for people who wouldn't even know what gravitational waves are, what is LIGO?
Right. So LIGO, like you mentioned, stands for the Laser Interferometer Gravitational Wave Observatory. It's a large-scale project aiming to detect gravitational waves. So gravitational waves are, I guess, like the bending or warping of space and time itself. So you have these massive objects in space, such as black holes, like you mentioned, and you can kind of think of them as like sitting next to each other or almost coming in contact with each other, and their weights are massive enough to bend this three-dimensional grid in space. So an example would be, I don't know if you've ever stood in a pool with like another person, and each of you start jumping at opposite ends, and these waves start coming in contact with each other from your masses. So that's kind of the same idea happening there. So what LIGO what it has done is pick up those signals, and though they're really far away, LIGO is sensitive enough to pick them up. So there's two detectors in America. One is in LIGO Livingston, Louisiana, and one is in Hanford, Washington. And they work together to pick up these signals, because you can't pick up a signal with just one detector. You'd have to have some sort of reassurance that you've picked up a signal. So having more than one detector creates a network to check up on whether it is a signal or not. And then there's other ones in Virgo, and they're creating another one in Japan called Kagra, and then they're also doing a LIGO India site. So there's a bunch of these detectors popping up all over the US to create a very large array of sensitivity, I guess.
So like for the array, I'm from my understanding, the more the better, in the sense that the more detectors you have, the more reassurance, as you said, for confidence in a detection, and also maybe coverage of the sky too, right? So I would assume more is better. Yeah.
Right.
Can you explain a little bit about how it works, how LIGO actually works? And I mean, yeah.
Yeah. So
go.
So the ones here in Livingston and Hanford are based off a basic Michelson interferometer. So you have a laser shoot down a tunnel, I guess, and be split into two ways by a mirror. And there's these other mirrors at the ends of the arm length. So LIGO's arm is about 4 kilometers each, I think, and it's shaped in an L. So when the laser is reflected back off of the end mirrors, you would see, if there was no warping of the light or arms, you would have those, the laser pattern merge back normally. But if there was a sort of a differential in the arm length, which is what LIGO looks for, you would see the signal come back in a photodetector.
So yeah, if you're measuring like essentially vibrations of a mirror, and this is, I know from your background and your research, this is very pertinent to what you have done and what you're doing right now, but I'm assuming a lot of different things can shake the mirror, and that's one of the reasons why you need multiple detectors that are separated at their conditions are isolated. So if you have a true signal and maybe somebody was chopping down trees near Livingston, you know that you could rule that out, right? Right.
So LIGO does a lot of what are called data quality checks. I don't know if it's fine if I jump into this already.
You could do whatever you want on the show. Anything is possible.
There are no rules.
So in each of the LIGO detectors, there are a bunch of sensors. So there's microphones, seismometers, you can name it, anything to pick up different signals of motion or sound that could be around the detector. Because gravitational waves are so small, by the time they reach us, we want to be as sensitive as we could against other noise and only to gravitational wave. So they have these channels, and what they use them for is to make sure, so they look for physical coupling in those channels, and if there is like a noise from, like you mentioned, a tree falling or a plane, they'll highlight it and say, you know, we don't want to look here. This channel is not good at looking for gravitational wave events. And a lot of the times there will be noise at one detector, such as an earthquake from, I don't know, Peru or something. Like, it'll pick it up, and we want to make sure it's not an event. So you look at the other detector, and you know what, they picked it up, or they didn't pick it up. So, you know, if one picks it up and the other one doesn't, then it's not an event, or something like that. So yeah, that's kind of how it works.
I think I've heard stories of like car crashes nearby, and I think there was one that was like a fridge or a microwave or some appliance that they thought was a signal, and it wasn't.
Yeah, there was one of like the funny ones was in Hanford. I think it was Hanford, but it was like really cold at one time. So, or no, it wasn't really cold, but so LIGO has to be really cold to work in a vacuum setting, and when that is running, the pipes outside actually kind of freeze. Like, if there's water on it, it will freeze the water. And at one point they had like this pecking, like this signal every so many seconds coming up in this one channel, and they're like, what the heck is it? Like, we can't be having this many events, like inconsistency. So they actually sent one of the LIGO fellows out to look, and it ended up being a bird or a crow pecking on like ice on the pipes. And they were like, oh, okay, that's what it was. And then, like you mentioned, there was a fridge. So in the LIGO sites, there is actually a kitchen area where you can like go cook food and stuff, because people are there like all night, so they need to eat. And there was this like noise at like a certain hertz range that was kind of weird, that was going on and off in the signals. And again, they're like, what is this? Like, this is too repetitive, and this is too weird. Like, is something wrong with our detector or something? And it ended up being when the fridge would turn off and on to cool itself. So like they got rid of that fridge, obviously.
Oh, they had to get rid of the fridge. I heard one from
Man.
Livingston was because there's like a lot of tree loggers nearby, and you could tell when the tree loggers would like take their break and go to lunch, because there'd be a sudden drop around like noon, and then it would come back around like 1 or 2 p.m. or something like that.
Yeah, when I was there, there was this train that would always pass, and it was like you knew when it was passing because you would already recognize the signal or in the data. And I don't know why that train was running, but it's like pretty close, but it would always run. And then like a few months later, that train stopped running. Like it doesn't run anymore. And you notice like you don't see that signal anymore. So it's kind of funny, like why is it there?
I mean, in the control room, they have like different monitors of like the different noise sources, right? And like the laser cavity noise sources, etc. And I always remember seeing the human factor had all of this stuff on it compared to all the other plots, right? Like,
right, the environmental noise, or the seismic.
Yeah.
So you work with data characterization, right? Is that what that is? Like, characterizing, because I always hear you say that, but I'm never exactly sure. Is it like, okay, this data is a bird, this is a human, this is a fridge?
Yeah, there's a few different areas of data detector characterization. So some people do scattering noise or scattered light. Others do other areas, and I work mainly on environmental noise. So like thunderclaps, trains, people. What I do is I look at the data mostly through the microphones, because that's the best sensor for me to actually hear something. We like create pipelines to pick up this noise and say whether or not it's actually a thunderstorm or not. And if it is, well, we won't look at that section of data, or we'll remove it completely. So one of the pipelines, or there's a few pipelines LIGO uses to determine if there's a gravitational wave or not. So one of those is PICBC, and there's another one like GST Lao, but I work mainly on PyCBC, which is a Python-based script for compact binary coalescences. So this one does a match filter system where you have a time series of data, and you run across a waveform, like a simulated waveform created by the mass and spin of the two objects colliding. And if it matches, well, you're like, okay, this should be a gravitational wave event. If it doesn't, it isn't. And then when you get a match, you actually get a ranking statistic of it. So it ranks it on how likely it is to be an event or not. And PyCBC actually uses the data quality flags, we call them, to determine this. So flags are glitches, or we call them triggers, in the data that shouldn't be a gravitational wave event. So if a microphone picks up this signal or this glitch, we'll say don't look there again because it's not a signal. And there's like actually a funny story is that when 1708-17 came, there was a glitch right on top of it. And when it was run through PyCBC, it removed that signal and it said there is no gravitational wave event here. But luckily
nothing to see here.
Yeah, luckily they had other pipelines running to check it, and I think GST Lao picked it up and said, you know, there is a signal here. So they had to go back and actually look through the data more to like confirm it was there. So
yeah. I remember seeing that plot.
Yeah, so like last year when I worked at Caltech, that was actually my project, was to fix that error. So I created like a new statistic ranking method. So instead of removing the glitch completely, it just re-ranked it compared to the signal. So like if you had a chart and the glitch and signal were right at the same level, after doing some re-ranking, it's a lot of math, but I can't explain it right now, but it would actually pick up the signal statistic and lower the noise in the background, so you would clearly see the event.
So that's like it's like something flagging signal to noise, right? Essentially, right. Like a ratio. I know you mentioned that like you're fitting template waveforms. Just for those listening, those waveforms that are being compared to with your data are all generated from theory. That's all numerical relativity. So you can simulate what two black holes of different masses and inclinations would look like in that data, and then I mean, do you know how do they just match one by one until one fits, or is there like a more complicated sorting patterns with that fitting process?
I believe they just run it through all the templates they have. So they have like a few hundred, and they have to test each and every one. And I know like one of the big things they're looking for right now is like the supernovae wave stuff. So they have simulated waveforms for those, but obviously you don't know if they're correct or if they're in the right metrics or not. So that's one of the big things going on right now to get a wave. Well, we have waveforms, but to get more waveforms from that, in case either LIGO or like a feature detector picks one up, we can match those.
So, I mean, I know oh, sorry, go ahead, Victor.
I was gonna say, so just basically to sum it up, two huge objects like two black holes or two stars just spin around each other until they collide and then create this huge explosion that eventually creates a sound on Earth, and LIGO picks up that sound. That sounds right? Like, did I butcher that?
No, that's right. I mean, I wouldn't say it's exactly a sound because you can't actually hear it. It's more an electrical signal that we can turn into a sound. So it's in the human hearing range, so we can like modify it to like be heard.
Yeah, I know at one point during that event that we had back in September, you made a really, really cool analogy with the guitar. When I first got on to the Zoom, Richard had his guitar out, and I wasn't sure if that was related or not, but that was the first thing that I thought.
Might still be.
Right. So those that weren't there. I made the analogy that LIGO works like an electric guitar. So when you have an electric guitar, if it's not connected to an electrical signal or an amp, I guess, and you string it, you don't hear anything, or you just hear like the strings plucking.
Right.
But once you plug it in, you can actually hear sound from it because of the currents being changed.
Now it is true, if you were up close enough to that black hole event, barring all other unpleasant circumstances, even though you're in the vacuum of space, since, as Brina said, it's in the audible range, the frequency merger, it would vibrate your eardrums and you would hear it.
Right.
But since we're just so far away, or in time, essentially in space, it's so weak at this point. Brina, how big is the LIGO arm? And what's the relative change we're looking at? Like, you know, because we're seeing these things from so far away, right? So they're weak.
Right, so each LIGO arm is about 4 kilometers long. You know, they actually had like a whole investigation, I guess, or something, I guess you can call it, to determine what a good length would be, because you want the arms as long as possible to create a more sensitive detector, but once you reach a certain point, Earth's curvature actually affects this. So I guess they settled on 4 kilometers, at least in America. And I guess the sensitivity would be to detect something like about the size, smaller than the width of a proton, I believe. Yeah. So it's very, very small. And a lot of people I know, like one of my other colleagues asked, like, there's a restroom in LIGO, why doesn't it pick up that noise as a detection, like when people flush or stuff like that? And I'm like, well, you're not looking in that hertz range. Right. Like you're looking for a certain signal, like in, I can't remember the exact range, but I think you can tell something that is terrestrial versus not.
Right. And I think after full advanced LIGO, the sensitivity is like a curve, right? And so like everything above that you can detect. And I think it's something, isn't it between like some couple of 10 hertz and I think peak sensitivity is 100 hertz, right? Or am I wrong? I actually forget off the top of my head.
No, I think you're right. I don't know if it changed recently or not, but that was the situation.
And my reason for asking is because I think it's in the range of power outlets, right? Because power outlets oscillate at 60 hertz. So like technically isn't there like a spike in the sensitivity curve at 60 hertz? Like that's where all your power outlets are. It's
yeah.
Interesting. This gravitational wave looks like a giant power outlet in space.
Can you guys talk a little bit more about the actual event that happened? Because I just feel like that part of it is so amazing. So the gravitational waves are the part of it that come here, but like what actually happens out in space? You mentioned it was, these are probably some of the most violent events in all of the universe.
Yeah, I don't know. Do you want to take it or do I want me to
I thought you're the expert, Brina. I'm asking you now. I could certainly answer questions if you want, but I'd much rather give it to Brina if she wants to answer it.
Okay. I know I mentioned a bit before. We have these. Yeah. Okay, go ahead.
No, you mentioned compact binary coalescence. What is that? That's a broad range of events, right?
Right. So those are most the objects that are compact. So you have like black holes, neutron stars. And they hold a bunch of mass in a very tiny object. So you can have a black hole like the size, like, I don't know, 6 solar masses, but it weighs intensely, like a huge amount. And since those two masses bend the space and time around them, their weights will eventually come together if they're close enough. So I know, like, if you have 2 people sitting on a bed, if one of them leans in a bit more, you'll eventually lean into them because you're so close to each other, right? Right. That's kind of what's happening. So their gravity's pulling each other closer and closer, and when they get close enough, they'll there's like these 3 stages where they in spiral merge. I forgot. And ring down, there you go. Those are the 3 steps. So they'll spin together, merge, and then you have this ring down of the gravitational wave. And when that happens, there is a new either if it's two black holes, you'll have a new black hole formed from those two previous masses. If it's two neutron stars, I think have another new, I mean, some funny stuff can happen.
It depends on their mass. If they're just to jump in there real quick, if the neutron star total mass, and like if they're spinning fast enough, they could have actually quite a high mass, but usually they'll probably collapse to a black hole if they're above a certain mass. So
right. So yeah, that's kind of what happens mostly. And it was like, it's funny because before you didn't know how many systems you had in space, especially with black holes, because you can't see them. So you didn't know how many pairs of black holes you had near each other. And then when you finally get these signals, you discover, like you find like recently, you have like 5 a week popping up, like just colliding. It's very catastrophic, I would say, but it's beautiful at the same time.
Yeah, there's something beautiful about it.
That is.
Right. But then knowing that you're hearing all of these mergers happening all the time around us, just kind of like a regular thing. Yeah. So Pi CBC, when you were talking about Pi CBC, that is code that is matching predicted what the signal of what we would predict to like black holes would look like of different masses.
Right.
And comparing it to data. When you say time series data, we're observing over time, and then we're getting a signal, right? So.
Right. Yeah. And there's a lot of parameters, but like the main ones would be the mass and the spin of the two objects. There's a few other parameters. I think there's like about, I can't remember if it's 15 or 17 in total.
Yeah,
but
something big.
All those parameters to create these waveforms. And I know like people I worked with over the summer worked on those to test them and to create new ones. So they're still being used.
And I believe it's harder to predict neutron stars, I think, because there's more physics that, like, there's more assumption. I mean, black holes are simpler intrinsically. I think like neutron star waveform models are harder to make. I could be wrong here. I'm not actually in that business, but from what I've gathered, I think it's even harder to predict those. Or there's at one point you can't tell if it's a black hole or a neutron star, so there's some degeneracy in the signal.
Mm-hmm. Right.
What other sources could you have? Like, what other gravitational wave sources aside from compact binary coalescence?
I know I mentioned like the supernovae situation. I'm not too familiar with that, but they call those the burst events. So events that create gravitational waves like on their own, I would say, from the reactions and the explosions they have. I can't think of any other ones off the top of my head.
So then basically, so LIGO has like a certain amount of sensitivity, and it's getting more and more sensitive, and so it's sensitive to black holes and to neutron stars merging. And so I'm assuming supernovae, because it's by itself is not as powerful as those two, and so I guess none have been detected yet.
I mean, we don't know. We don't know if we've seen them or not, because we don't have the waveforms. We don't know if we have the correct waveforms, for one thing. Also, we don't know if we're in the right Hertz range to look at them. There's a couple of different factors that when I say we, I mean me, that we don't know yet.
Not us, just
other people probably know, not me.
Yeah, and those supernovae are hard to model because they're called threshold events, because like, okay, so we don't know what the shape of their waveform would be. We could only essentially say, oh, they're probably stronger signal than a certain amount, and we'll try to trigger that. But depending on the shape of the supernova, I'm sure, and yeah, Victor, you're right, the supernovae are going to produce a lot weaker of a gravitational wave signal than a compact merger.
Yeah, could you talk a little bit about that's something that's really interesting to me, the different observations. And so there's different runs that LIGO does, and every time it gets a little bit more sensitive, right?
Yeah, so I can't remember the exact year they started, but I know they started around, they had O1, which was the first observing run, and they didn't pick up any signals from them because they didn't have enough sensitivity. And then they have these, can you remember what they're called, Richard?
Like engineering runs and
the engineering runs.
Yeah, there's like O is your observing run, and then in between they like shut down and they have upgrades, right? Is that what you're talking about?
Yeah, I couldn't remember the name off the top of my head, but between those, the main observation runs, they have engineering runs, so they bring in new materials or new, I guess, I know at one point they replaced like the mirrors in the detectors, and they replaced like the fibers that held them up and whatnot, just because they learned that one does better than the other, or the laser bent one mirror, or something, like some other things, like a lot of stuff happens. So when they do these engineering runs, they test the detector to see if they improve the sensitivity or not. And it was funny because 150914, did I say that right? 150914? Yeah. Yes. Was actually, I can't remember, was actually picked up during an engineering run. So like the first detection ever was picked up then, and they were like, oh, is somebody pulling a prank on us? Because, you know, some people, the scientists at the site actually do injections. So injections are tests of the channels and of the detector to see if it's functioning properly. So they had to question that. When they get an event, they have to question it very seriously, because you don't want to be saying one thing and then, you know, it's not a signal. Right. Especially during the engineering run, they had just turned on the detector and you get the signal and it's a little questionable, you know. Like, I know a scientist at Caltech mentioned like he wanted to disprove this just because like he couldn't believe it. You know, like, yeah, I think that's being a good scientist, you know, you want to question your own work to the fullest and not just say, oh, look, we got the signal, like, I'll take that. Like, you don't know, like, you don't want to make a mistake. But so they had that, and then O1 came, and I don't believe, did they pick up a signal in O1?
Oh man, I'm gonna lose scientific credibility. I don't remember. For all the astronomers listening, I've done follow-up since 02, so I wasn't in the 01 era myself.
Okay, so anyways, we can skip that. So then 02 came, and then it got a bit more sensitive, so we picked up a few more signals. I think 170817 came during 02, and then each run lasts about a year or so. So you start one day and you end on that date the next year. So then after 02, you had the third or next engineering run, and you add more upgrades to that and you keep improving the detector. And then 03, which was it was 2019 to 2020. That's when LIGO became really sensitive. You know, you have advanced LIGO now. And you're picking up at least the black hole mergers like 5 times a week or like twice a day. And by then you kind of know more what you're looking at because you've had some signals before then. So like right now they're doing upgrades as we speak. They had actually moved like some of the materials from Hanford to Livingston, and then they're working on CAGR right now, which isn't LIGO, but I know they're doing that. And I guess they're testing right now. I can't remember, but yeah. So then we have 04 like coming up soon. I don't know the exact date, but yeah.
That's cool. So I honestly, I think I don't know all the details, but I just, the history of everything is, you know, in terms of LIGO and gravitational waves is really interesting. I reached for this book because for some reason I had forgotten, but it just hit me. I want to read something about the 2015 one, and it is from a book called The End of Everything, Astrophysically Speaking, by Katie Mack. And this starts off chapter 7. Chapter 7 is called Bounce. And it says, On September 14th, 2015, at 9:50 a.m. and 45 seconds UTC, you were, for the briefest moment, just a little bit taller. The gravitational wave crest that washed through you had been traveling across the cosmos, warping space itself in its wake for 1.3 billion years, ever since it was set off by the violent merging of two black holes, each 30 times more massive than the sun. You might not have noticed the boost. After all, you grew by less than 1/1,000,000th the width of a proton. But physicists at the Laser Interferometer Gravitational Wave Observatory did. The first detection of gravitational waves was the culmination of decades of a long search, requiring the development of new technologies and the creation of the most sensitive equipment in the history of experimental physics. Finally, detecting those ripples in space-time was heralded by as the ultimate vindication of Einstein's general theory of relativity.
Beautiful. That was Katie Mack, right?
Yes, that was astrophysicist Katie Mack. Great book. It's called The End of Everything, and it's about, every chapter is a different theory about how the universe is going to end. So, yeah.
That's awesome.
Yeah, it's a great book. But can we talk a little bit about that? How she ends it talking about Einstein's theory. And you were saying, I thought about it because you were saying how that there was that one physicist who really wanted to disprove it. And I mean, even Einstein did not believe that it was going to be detected, right? One of my favorite things about that is hearing how he predicted gravitational waves, but he said something along the lines of, yeah, they probably exist, but I don't think humans will never find them.
Yeah. So when 1509-14 did come out, there was a big controversy, I guess. So when, they kind of confirmed this event and they were getting ready to release the papers, they asked the people there at those sites, like, do you want your name on this paper or not? Because it was such a big announcement that, if it may had been proven false later, you have that in your history now. And I know a bunch of people actually left, like the collaboration, or like they couldn't agree to having it be a real signal. So I don't know, it's crazy.
It is, like, because I mean, it had never been detected before. So I mean, they're looking at it and they're like, right. it worked, but did it? I mean.
Also, the signal was able, Brina, you mentioned it was during an engineering run, and the signal was visible and the waveform was visible before any processing of the data or like noise reduction was even done. So just, I'm trying to build a little bit bigger of a picture of like, why were people so skeptical? It was also at a time it wasn't expected, at a sensitivity we didn't expect. The signal was super strong. You could see it before there was noise processing. So like, no wonder it seemed like not a lot of people could believe it at first. So.
Right, and it's still one of like the loudest signals to date, which is crazy because even though we've ramped up sensitivity since then, we've become more sensitive to other noises that aren't gravitational wave events, but you should also pick up the noise from events. So it's still pretty mind-blowing.
Yeah.
It is.
Go ahead, Victor. You sound like you're gonna say something.
I was gonna say, I also read something really funny about in 2015, before they released it, like before they actually announced it to the world, that they had some like indoor party, and the way that it was leaked was there was like a cake from NASA, I think, that said, "Hey, congratulations," and somebody tweeted that, and that's how the world found out.
Yeah, and it's also funny because I wasn't there at the time, obviously. I was still in high school, but I heard stories from the people there that day that they were celebrating with the cake, Neil deGrasse Tyson went, and I think they were doing like a tour of the observatory, and they saw the cake. Like the cake was right there in front of everybody, and they're like, "What's the cake for?" And I think someone like said like, "Oh, it's someone's birthday or something." Like, we don't know. So like they had to really keep it like to themselves. Like, I don't know if I could keep that secret.
Also 170817 was leaked too. It's funny how there's like, in science, there's like leaks of things before they happen. I think there was a tweet that got sent out before the announcement, and 170817 was the first neutron star merger. So it happened 2017, August 17, and this one tweet basically triggered a bunch of amateur astronomers to look at all of the manifests of all the high energy satellites, and they were like, Fermi, Swift, Hubble, all these other satellites started looking at this one galaxy. I wonder why they're all looking at this one galaxy, and they started to put the pieces together. But it's just, I love these types of stories. You hear like all the time, human nature. We want to get that out and talk about it. So.
Yeah, I know. Like with music, like with albums and stuff, at least maybe not for bigger, but like for smaller bands, it's a very common thing that when an album's being worked on, there's a lot of people that work on albums, and at some point, one of those people will just show it to a friend and say, hey, check this out, and that's how things get leaked. And I guess even in the science world, it's kind of the same thing. I mean, there's so many people working on these experiments and finding these out that when you detect the first binary neutron star merger, there's bound to be one person to tell a friend or tell a colleague or somebody like, hey, guess what we did? And yeah, that's just going to lead to a chain reaction of leakage. That was a weird
That's
word
not
choice.
that is not the title of this podcast. A chain reaction of leakage is not going to be the.
Yeah, I know people told me I couldn't even tell my wife why I had to go to work at 3 a.m. because of a signal or something. Like they had to keep it to themselves.
It's a birthday party.
Yeah, we're having a birthday party.
Brina, you remember
to work at 3 a.m. It's a really important birthday party. Okay.
It's the birthday party of a new black hole. But I mean, when Toros participated in getting the optical counterpart, I remember we weren't able to say anything for a while either, especially when the data first came in and we were looking at it and it's like, oh, yep, there's an optical counterpart. But we like the memorandum of understanding was we're all going to release our scientific reports at once. So all 70 something observatories are going to publish at once. That's when we're going to announce it. And until then, don't tell your friends, don't tell your wife or your kids or
your dogs, cats.
Yeah, the cats know already, but the dogs don't tell them,
Yeah, cats know things before humans for sure.
Yeah.
They're the ones that told Albert Einstein about gravitation. So I think that's a pretty good segue into talking about a little bit more about the university and the Center for Gravitational Wave Astronomy and all of our great friend Dr. Díaz and the gravitational wave observed in 2017 and multi-messenger astronomy. Lots of things there, so I'll just leave it to you guys now. Go ahead.
Oh, wow. Brina and I were both like, no.
No, sorry, let me just set the stage a little bit more. So, sure. A big reason for the South Texas Astronomical Society is there's a lot going on here in Brownsville, in South Texas. There's so much going on. We have SpaceX here building Starship on Boca Chica Beach. They're already doing testing. That's huge. The first interplanetary spaceport. But also, I mean, we're not new to space and science, and the university and Dr. Díaz and you guys have played a huge role in this thing called multi-messenger astronomy. That's one of the most groundbreaking fields. Just one of the coolest things going on in science right now. Merging black holes and neutron stars, and we have an observatory here that played a pretty big role, and you guys have played pretty big roles here. So yeah, can you talk a little bit about that?
I'll leave this to Richard actually, because I wasn't here in 2017.
I mean, Brina, though, I do want to say that you were here during a majority. I would say the peak activity of CTMO especially in relation to this type of work, like following up transients. And we just dumped a bunch of words out there for people. So like multi-messenger astronomy, transients, what are all these things? What is CTMO? You've heard us say all this stuff before. Long story short, and I should let, Brina and Victor talk about this too, but the detection of black holes, neutron stars with LIGO in gravitational waves was essentially the gravitational analog to when Galileo first turned the spyglass to the sky and it became a telescope. And this is a new window on the universe that optical, radio, all electromagnetic is not privy to. So now you have essentially two messengers. There's other ones, but let's just say right now, E&M, gravity. It's the first time in history that we can observe the universe in both of those things, carrying completely different pieces of information, but when looked at together, builds a more comprehensive and integrated picture of an astrophysical event. So multi-messenger astronomy, it's a new era, last 5 years, 6 years. Essentially, it's the era of having multiple messengers or these force channels speaking to you from the heavens. It's not, I know Victor would like that, but it's not just photons anymore. It's also geometry. So the role CTMO has is to train students and teachers to do a lot of these scientific objectives, but one of those big objectives is to follow up transients. So like anything that happens in time, either really briefly or something that changes in time in the heavens, is a transient event. And gravitational waves are transient events. They occur and then they're done. But they're caused by events that could potentially have other information that other telescopes could see. So like CTMO will respond to gravitational waves, try to look at the spot from which it came and see if they could see the explosion that caused the visible explosion, let's say, that caused the gravitational wave event. Okay, so Brina was there from 2018 onward. So 03, essentially, there was a lot of responses. CTMO at that time was responding to LIGO triggered events the most during that time. 2017 was a big milestone. It was the first time two neutron stars were seen merging, and it was observed in every wavelength of light from radio to gamma. There was a gamma ray burst, there was X-ray, radio, optical, all that. And since then, there's been multiple neutron star mergers and even a neutron star black hole merger. But CGWA, Center for Gravitational Wave Astronomy, plays a central role in all of that. That's the center at UTRGV that coordinates the observatory. It's also the hub, the representative hub of LIGO. So like through CGWA, Brina was able to work with LIGO Livingston and go to Caltech and do these things. And it just so happens that CGWA houses some of the largest contingent of LIGO scientists in the US, rivaling MIT and Caltech. So a lot of the scientists that still are there, some of our professors who are teaching Brina and myself, developed a lot of the initial stuff in LIGO. So yeah, I tried to give an overall picture. I don't know, Brina, do you want to add anything to that? Like your perspective, or did I miss something?
No, I think it's just interesting because, we aren't, like, CTMO isn't the only one working on LIGO. There's other groups. So, like, we kind of all come together under the Center for Gravitational Wave Astronomy. You have the people that work on the optics, or the people that work on the burst signals, and then you have the detector characterization. So, like, it's pretty cool. In such a small university, you have a very large amount of people from the collaboration.
Mm-hmm. Those first simulations, just real quick, just for some history, I think the first successful black hole merger simulations were done by Campanelli, and she was at UTB when this occurred. I think it was like 2003, 2004 or something like that. And so like that's just an example from a theoretical. You mentioned instrumentation and optics. There was also theoretical stuff done there. I know Joseph Romano, who is a pioneer in the stochastic gravitational wave background, which we can get into. That's another source, but that's more complicated. Developed a lot of stuff at UTB at the time. So yeah, you're right. It's just like CGWA is like this hub, and there's all of these different pieces contributing to LIGO, including the multi-messenger outlet, the optical stuff as well.
what blows me away is the dedication that they, the dedication that they kind of need, because I mean, I hope I get the timeline right. I'm not going to say the exact date, but I know around 2000, the year 2000 was when CGWA was started, and then I think in 2002 was when they received the first big round of funding from NASA, from the University Research Centers grant. And that's what kind of kicked off that program. But 2002, that's still 13 years before the detection from 2015. And then, and I mean, it was 2 more years after that until the first detection where multi-messenger astronomy was possible. So that's a lot of years to be, dedicated and to be continuing to do research on something where, I mean, I don't know. What if LIGO never would have detected that? Like, it's crazy how physics and these sorts of experiments are really just a gamble almost. Well, not a gamble. It's not a gamble, because gamble is based on just chance, and I guess physics, it kind of is, but it's also, I mean, you put a lot of work into the theory, so it's not, I guess, right. You can't completely compare those.
I mean, it's a educated gamble, maybe, if anything. You're trying your best to look at the evidence and to interpret it very carefully. That's why, I mean, when LIGO made the first detection, no wonder. I mean, it's for something. Let's speak to your Carl Sagan fandom as well as mine. Extraordinary claims require extraordinary evidence, and to claim that we have detected gravitational waves and the first black holes in one measurement for the first time, where a lot of people are already skeptical about it. Like, no wonder there was a lot of hesitation.
Apologies for the dog barking earlier.
I mean, maybe your dog that was a very insightful comment that needed to be added to the podcast.
But I wanted to mention, like, it was crazy because, when I worked at Livingston, I still work, but I've met people that have been in LIGO since it started. And, like, even since I was born, like, it's crazy to me to think that they are dedicated almost like their entire life to this one project.
Yeah, like, it's a multi-generational family. Like, you must be maybe 3rd generation or 4th gen. I don't know how it would work, but yeah, that's awesome that you're continuing that, and you were there at the culmination of the discovery. Like, this is all coming to fruition right now, and you're right in the middle of it. You're working with the people that have been involved for, like you said, quite a while. That's amazing.
It is. So can you talk a little bit more about the process of the I guess you, the research part of it, the research part of multi-messenger astronomy? And so it happened because, I mean, I guess more of the specifics about, so this explosion happens, when there is a neutron star merger, because if 2 black holes merge, well, they eat up all the light, so you don't really get much. But if it's 2 neutron stars, you get a nice explosion. And so how long does that stick around, and what kind of data can you get from the observatory, and why does that matter?
Is that to Brina?
That's to both of you.
This is just like Stars on Tap, where somebody would ask Brina a question. She'd look at me in the audience and be like, Richard. I'm like, okay, I could say this. Okay, so just let's look at neutron stars, right? 2 neutron stars merge. The gravitational wave happens at the beginning so we mentioned that LIGO peaks at 100 hertz or something like that. 100 hertz, that's 100 cycles per second. So what that means is when the black holes are getting closer, they spin faster. When they're going around each other 100 times a second, LIGO can detect that at peak sensitivity. That's what that means. Okay, so when the neutron stars are producing gravitational waves, that's right at that merger, and then they merge. Okay. And then a lot of stuff happens in quick succession. 2 seconds after merger, at least from the first detection, you have a gamma ray burst if it's pointed towards you. So gamma ray gets picked up. There's it's like gravitational waves. 2 seconds later, pop, little gravitation gamma ray burst. if you're sensitive enough and you have a low frequency radio array, you could pick up a radio burst as well, because the two neutron stars are moving so fast that their ejecta, some of it achieves escape velocity and gets flung out tidally, which is a rapid deceleration that produces radio waves. Okay, so you have radio, early ultraviolet, and early gamma rays. Then for about a couple of days to a week, you have optical and infrared out to 2 weeks. And then after a month or longer, you have X-ray and radio wave emission, as that cocoon of exploding material slows down and produces radio emission in the interstellar medium surrounding the environment. So if you're, so right there, I said a lot, but basically 2 takeaways. All of that information comes from so many different channels, and those channels occur at different time scales. Like if you're not looking at the right time, 2-second short gamma ray burst, you'll miss it. Radio waves appear and they peak, like we didn't see with the very large array. Dr. Alessandro Corsi, who's at Texas Tech University, did the radio follow-up of GW 170817, and they noted radio emission not very strong right after the event, but after a month, the radio emission actually got higher and higher and higher. Whereas they're still seeing it, they still saw the radio counterpart to GW 170817 a year later. And because that cocoon is just expanding. It's like a supernova, like that you could see a supernova for years because it explodes, and then you're just watching that explosion get bigger, and it's just moving into interstellar space. And a lot of stuff happens in between the explosion and it getting to be very big and diffuse. So CTMO CTMO is a member of TOROS, the Transient Optical Robotic Observatory of the South, which is a network of telescopes. There's multiple collaborations like TOROS that does this, but basically what CTMO would do in this whole picture is gravitational wave is detected, LIGO sends an alert, we get the alert, we know roughly where it came from, and we point the camera and we just take pictures in that region and see if we can find a transient, a little explosion optically. So that's where the role of CTMO is in that whole picture.
Yeah, so what does it mean when you can get data on the explosion? And so lining up what you get from LIGO and what you get from CTMO.
Yeah, you get a lot of different pieces of information. So like the gravitational waves will tell you like the mass of the system. It'll tell you their angular momentum, or at least to some degree of degeneracy, like there's some uncertainty there. And but if, let's say you detected an optical, the models of these processes give you information along different channels. So like optical emission tells you how fast your fastest ejecta is released. And depending on the number of components, like in a neutron star merger, you can have ejecta moving at 70% the speed of light initially. Optical will pick that up. The infrared and optical will also tell you the time evolution of it. So if you take a picture every night, actually you'll probably have to take a picture every hour, because kilonovae, which are the optical counterpart to neutron stars merging, they last optically only a few days. So as you see that light change in time, and you see it in different colors. So let's say it's really blue in the beginning and then it turns to become really red at the end. That tells you about the radioactive decay of the material in the ejecta. So like, and that's just optical. Radio tells you stuff about the speed and mass of the ejecta. X-ray tells you stuff, and it all comes together as one comprehensive picture. It's beautiful, wow. Really. That's why that's the field I'm in. I mean, Brina and I are in that regard the same field. We're working in different channels, but Brina's working in the gravitational wave regime, and I'm the one that gets the trigger from all that hard work. And I'm like, okay, now it's the optical people. We have to go look for the explosion. It all comes together as one picture.
Yeah, multi-messenger. It's really beautiful.
Multi-messenger.
And sorry, I keep expanding this broader, but
this is awesome.
No, I had seen like phrases that explain like, well, what does that mean? And they were very, very like, so you have that data, you can get all this data, but really what does it lead to? And something that kept coming up was we study the origins of the universe. Basically, we study these events through finding out all of that and getting all of that, those little pieces of data, and putting different types of data together. We can find out more about the Big Bang and just the origin and birth and death of the universe and black holes all together. So can you talk a little more about that?
Brina. I'm not being interviewed here. Just kidding. Nah.
This is an interview. I thought we were just having a conversation.
I'm just kidding.
I don't know. I feel like I'm more just on the gravitational wave side, so I don't know if I can say the right words for this.
Well, how about this? The all of the engineering that goes into LIGO, right? All of the advancements in the detector capabilities. You know, not just the astrophysical implication of what we're looking at, but I'm sure there's a lot of applications for all the engineering feats that go into detecting something smaller than the width of a proton. I mean, the amount, I feel like that's nothing short of magic, really. Like, I mean, I know it's physics, which is essentially magic, but right, like, have you come across, when you're working with people at LIGO, talking about like even applications to society, or like how that engineering benefits people?
I feel like I have. I don't know how to quote them though.
That's all good.
I know like a bunch of times in the the seminars they give or stuff, there's the question that people ask them, like, well, what is this all for? Like what is the reason for all this? And like they normally answer, you know, it's for science. Like it's just like, what else do you want us to answer? Like
whole answer, science.
Science, you know, for the sake of science.
Curiosity's there. Why not reach out and like see what we can get from it?
Right.
You know, we always want to advance in anything we do and learn more. So like, you know, not even 10 years ago we knew, or not even, how many, 6 years ago or so, we didn't even know gravitational waves existed. And now that we do know they exist, we can do so much more. You know, the upgrades that we do in LIGO or stuff, we can apply those to other things, like you mentioned. And, you know, with one piece of information, you learned that these counterparts last this long, or they exist. Yeah, I don't know.
I mean, no, that's exactly spot on. I guess from an astrophysical perspective, I know, Victor, you said about the origins of the universe. In principle, now that we could see gravitational waves, we could see farther back in time than just with electromagnetic information. We know the origin of some elements now that we didn't know before. Like, we know where gold comes from now. We didn't know where it came from before that. And something that I haven't heard before, but I think just from practice and observation, is that the ability, like, there's so many papers coming out on how to respond quickly to things now that we're in this new era. Like, how does the telescope system change? How do people react to these things? Machine learning is important in there. So it could be even as far reaching as planetary defense from an asteroid, right? Because asteroids are transient events. So like, if telescopes are getting better and better at responding to quick things, then suddenly we could respond to even potentially earth-changing things. So there's a lot. They're very kind of scattered, but there are a lot of applications to this whole thing that greatly benefit humans.
Yeah. So not to get more metaphysical and philosophical again, but no, when you mentioned that answer about, you know, science for the sake of science, it made me think about I was recently listening to the newest Joe Rogan, Elon Musk podcast, and they brought up the big question, you know, what the meaning of life and all this stuff, and Elon said something that I thought was kind of interesting. He said that, you know, like the universe could be that it's the wrong, that basically we're asking the wrong question, that the universe is kind of the answer and we're here to kind of understand it, but at the same time the question, what is the meaning of life, is a little bit we're not there yet, because we don't know the right question to ask. So when I don't know, that's kind of what I thought of when you were saying science for the sake of science. Like, it's there and we're studying it and we're understanding it and we're learning things as we go, and we don't know what we're going to find, but maybe that's the point, that maybe we'll discover something that we never even thought to ask about, and yeah, that would lead to a better understanding of ourselves and our origins and our place in this violent universe.
Yeah, I mean, like there's been not like for LIGO, but there's been other experiments in science that have led to answers, not even on purpose. You know, you have accidental answers. Sometimes you don't get the answer you were looking for, but even though it wasn't the answer you're looking for, it is an answer to something.
Yeah.
Yeah, like the cosmic microwave background, wasn't that found like completely by accident?
Yeah, the same birds that were pecking at the vacuum tubes of LIGO were the ones that left the bird droppings on the Bell Labs antenna. No, just kidding. But yes, that was discovered by accident. Just, you know, Penzias and Wilson, I think it was 1965, working out of Bell Labs, New Jersey, and they were picking up this static that was isotropic, meaning they pointed their radio dish at every single point of the sky, and they couldn't remove the source of signal. They found bird droppings on the radio receiver and they cleaned that off. It still didn't do anything. And they realized that signal was the echo of the Big Bang that they were picking up in a poetic sense. But I also want to say to your point, to both of your points, because you both spoke on this, is that, you know, we don't really fully understand even what it means to be, you know, human or conscious, and why we're doing the things that we're doing. But at this point in time, it might have to be sufficient to say, well, plants, it's in their nature to convert to through photosynthesis, convert photons to sugar. It's in a dog's nature to bark. It's in humans' nature to always be pushing forward in the frontier. And we don't know why, or at least we have ideas, but we don't know why we do it, but we're doing it. And it seems to be, so far, that the more we do that, there's a lot of, there's a revolution in understanding. Has a lot of detrimental impacts, but also a lot of beneficial impacts as well, right? So I always think of the atomic bomb when I think of like the ultimate example of the benefit and detriment of a scientific discovery, because for one, you can have such human horror come from it, but at the same time, you have the ability to take you to nearby planets and to basically solve the energy crisis if you did fusion. So like you have salvation in one hand and the destruction in the other, and they're both from the same discovery. That's like the penultimate example that comes to my mind, at least when we talk about stuff like this.
Yeah. Even Carl Sagan and Pale Blue Dot, which I'm still not done with yet. I haven't had a lot of time to read. He's
Episode
talking
62.
I'm on the last chapter. You know. I was reading a chapter about asteroids, and yeah, he was. I mean, it's crazy how back then in the 80s and 90s, all these thoughts were already being formulated, and I think he was such a imaginative person, and he was talking about like asteroid deflection technology, and you know how in the future we should get to a place where if we find out there's an asteroid coming to us, we need to have the technology to be able to go to it and deflect it, whether it's like a bomb or yeah, whatever way. But how scary it is that we also have to worry about, well, if humans, if we end up smart enough and technologically advanced enough to build technology that can deflect asteroids, we have to also be careful that humans don't use that same technology to kill each other, to blow up another country. Or it's like, we don't want it to happen, because you never know when somebody's going to rise up crazy enough to use it on another country. They even talked about the potential of using asteroid deflection to hit countries, which is insane, because he said, and it's just, yeah, things he threw out, but it's scary.
It's scary, but then you have bold people that I think the boldness in science, at least in my experience, and I think Brina could say a lot about this too, is pushing in a direction that you don't know how it's going to turn out, and you could put all of your resource into it. You could sacrifice your social life, your sometimes your mental sanity. You don't get a lot of sleep. You're studying for exam, but you're pushing forward in an area of research that might not ever even be the correct thing. Like you might have a theory that just doesn't turn out to be correct, and that's the risk. So yeah, there's a whole there. It does require an ounce of courage, not only for that, but also for, well, what does the implication of my discovery mean for humanity? Can you imagine how Einstein must have felt after seeing the implications of E equals mc squared? Like that like, it just, to everybody, that's a popular equation, but to a physicist, that is a huge insight into nature. That there's so much untapped energy and matter that you could release it, and it would be catastrophic if you released it. That's I mean, that's a huge weight on someone's shoulder for discovering that.
Yeah. I feel like the podcast just took a very dark turn. We're now entering into the dark part of the podcast.
But this always seems to happen where, like, the last episode we were talking about dinosaurs and Yoshi, and then we talked about anxiety and so I know you talked about, like, I kind of getting back to LIGO a little bit, but how you got involved. You talked about that, but what was like you spent a couple of times at LIGO facility, right? When you were at Louisiana State. Right. Tell us about, like, some of the daily life. Was there, like, what was did you have like a 2 a.m. shift? Like, what was it like working with people at the Livingston site? Like, let's bring it back to a little bit of a positive thing here.
It's interesting. For one thing, I felt like the youngest person there because everybody was like either a grad student or like they've been there since LIGO started, like I mentioned. So it was kind of funny because I felt like their child that was just playing around in the detector and trying to figure out what they were doing. But it was nice because I didn't have to work at night, thankfully. I didn't have to be there at night. It was just daytime visits and whatnot. But it was interesting because I had the opportunity to just look at stuff there and ask the questions right there, like, why does this work? Or why are you doing this? Why are you breaking this instrument? Like, such, like, things like that. And the people there are so knowledgeable. Like, I couldn't imagine myself ever being as smart as them, but then again, they've been working on it since the 90s or the 80s. So, like, they're like the masters of this at this point. And it was fun. They taught me a lot on how to communicate the science they're doing. And even if it wasn't intentional, they gave me a lot of information that I didn't even ask for and didn't even think I would need to ask. And they were really nice about it too. Like, they won't like ridicule you and like tell you, like, that's a dumb question, like, why are you asking? Like, no, they're like really open to all the questions you have, no matter how small they are or how like weird they seem. And I don't know, it was really great. I know, like, one of my favorite things there was the tours that would happen. So they have at Livingston, they have like this education center, and you would have like schools go or people go and the public to see like physics demos in the building they have there. And it was interesting to see the people connect gravitational waves and like the detector to those small physics demos. And I know, like, one of my friends that was there with me in the summer, she's from another university, but she worked with me, and we were working on the project with thunderstorms, right? So we had to characterize these thunderclaps. And one day that we were there, she was helping the tours go on, and there was a thunderstorm, coincidentally. So the people actually asked her, like, do these thunderstorms affect the gravitational wave detector? And she was like, well, like, you know what? I have a lot to say about this. So it was fun, being able to answer their questions. Yeah.
I had a like a kind of a specific question about thunderstorms, but did you collect the data by essentially having to mic up different parts of the detector, or like how did you go about actually collecting the data?
Right, so I was in charge, so there's three of us. I was in charge of the part of creating the feature extraction code, and then the other two students worked on a location code to tell where the noise was affecting most in the detector, and then the other one was to actually detect where the noise was like coming from. What I had to do is, since there was I was lucky enough that there were so many microphone channels already, I didn't have to do anything. I just had to get the data. But one of the, I think like the most fun parts of it was that I had to create a script to actually hear the data from the microphone. And I sat at a desk for a couple of hours and ran through each segment that I wanted to look at and determine audibly if it was a thunderstorm or not. And of course we had like the dates when thunderstorms happened and when they didn't happen, but it was interesting to hear like what was going on in the detector without people knowing.
Interesting.
So when we get that, I would separate like it's not a thunderstorm versus it is a thunderstorm or thunderclap. And from then we just made it into an algorithm to test. So then we extracted the features using my code, which it was nice because at one meeting we had to give updates on our project at the Livingston site, and I was giving mine, and I compared it because I used a system very similar to Shazam. I don't know if you know Shazam. So like you hold the button down and it like listens to an audio of music for like a couple seconds and it'll tell you what song it is. So I did something very similar to that in my project, and a scientist there was like, man, that's really interesting because I always thought of gravitational waves as music from like the universe. So I was like, oh yeah, that's kind of funny.
So cool. Like, you got one saying like, Rihanna, and you got the other one saying like, supermassive black holes violently colliding 2 million light years away.
Oh my God. So LIGO is just a giant Shazam. Is that what you're telling me? It's like a Shazam for the universe, right? Like, oh, that's a thunderstorm.
I think we have our title candidate. The giant Shazam.
Yeah, so that was really fun. And then so I'm still working on that. And it's really, I don't know, it's nice.
And like, not to dive too deep into the technical stuff, but I am really curious to understand more about this. Like, what are there like general principles that you went by when you were designing, like what features you're looking for in a thunderstorm? Or did you notice something after listening to so many thunderstorms and looking at the data? What were some of the common things that you could kind of extract from thunderstorms, and you would know, okay, thunderstorms possess this where other noise sources do not?
Yeah, so we did have to filter it using, their signal to noise ratio. We wanted it above a certain value, and then we made sure, they have to last longer than 6 seconds at least, or so, like give or take. And then from there, I had to use, in the package I used, there was different features we could extract. I won't go into them because they're kind of weird, but we had to make sure we picked the right ones and make sure they worked. So I think I ended up using 6 originally to extract features or like data points from the audio in the time series. And then now we only use like 4 because they do around the same job and we don't have to do as much. And I guess it's just a lot of testing. So like when we actually ran it and tested like, oh, this is a thunderstorm or not, we would have to go back and listen to it and make sure it actually tested it right or not. And like we ended up getting like a 98% like correct response, at least then. I don't know how good it is now. I think it got better, but yeah.
I see. That's awesome. Wow.
Well, it's funny because you said thunderstorm, so I figured we can make this like a lightning round kind of thing. I wanted to bring it back. So I before the yesterday I put I let people know on social media that we were going to be talking about black holes, and so we had a question, not a lot, but my good friend Alex Zamora asked a question. But I think before that, maybe we can take it even way back. You know, we've talked about black holes and colliding black holes and colliding neutron stars, gravitational waves, and LIGO. But let's take it just briefly back to the basics and what is a black hole and how does that work?
Oh gosh.
I'm gonna mute myself. I'm gonna be.
What is a black hole?
I mean, I don't know how to explain it other than it's a massive object like that doesn't emit any light, but instead it actually pulls in all the light around it and envelopes everything around it because of its intense gravity. So I know we hadn't seen a black hole until recently when the Event Horizon Telescope released their image of a black hole, and you just see this ring of light around a black circle. So I think that's really cool because you had these predictions and these artist renditions, and when you actually get the data, you actually saw that it was what you thought it was, at least.
Yeah.
And I think there's a couple of ways that the black holes are formed. So you have the dying stars. If they're massive enough, when they're collapsing and it can't contain its mass or energy, it will collapse into itself and then it forms a black hole, other than a dwarf or a white dwarf. And then you have the creation of newer black holes from the colliding black holes, previous black holes colliding, you get newer black holes and so on. And then there's there's other ones we don't really know the origins of yet, just because we haven't gotten any data from them. So there's a couple of types. There's supermassive intermediate black holes, which we just kind of learned about recently, a few theories of how those are created. And then we have what are the other ones? I'm blanking right now on the names.
Supermassive.
I said supermassive, intermediate,
primordial,
and then those are the ones that are believed to be created at the origin, right, at the beginning of the universe.
Oh, so, those are essentially your primordials, but yeah. The ones that are currently 1 billion solar masses, and we're how did it get that big? We have no but I guess not all. LIGO couldn't detect all of these classes of black holes, right? So what would you need to detect, for instance, the gravitational waves from a supermassive black hole? Do you know what type of detector that would be?
I mean, I'm not too sure on what the range of the hertz would be that we'd have to look at, but I would think we'd need a space-based detector maybe.
Yeah.
I'm not sure if the ones on Earth could catch those just because they're so far away also, so I don't know how strong the signals would be.
Yeah, I know for the, so LISA is going to be your laser interferometer space antenna, ELISA, which will eventually be essentially, it's LIGO in space. And it's a triangle instead of an L for physical reasons. And that would be able to detect, for instance, I think your intermediate mass black holes, and definitely your white dwarf binary mergers, which you can't detect with ground-based. But to detect a supermassive black hole or primordial signals, not just black holes, but your stochastic background, the first gravitational waves produced by the universe, you would need pulsar timing arrays, which are essentially galactic scale detectors. But in principle, with primordial waves, you could see as far back in theory as when gravity split from all the other forces and behaved distinctive to them, your first decoupling, that's about 10 to the minus 21 seconds after the Big Bang. So light, you could only see 380,000 years after the Big Bang. That's when you hit your microwave background. To see beyond that you have to see with gravitational waves. But you would need pulsar timing arrays and space-based detectors to see stuff like that.
So the gravitational waves are basically the only window that we have to the time before the cosmic microwave background?
Yeah, because any information carried by photons, no matter what the wavelength is limited to your microwave backgrounds. Anytime before that, light could not decouple from the matter. The matter was not diffuse enough to allow photons to move around quickly. So, and far before being reabsorbed. So, but gravity has existed as gravity, as far as we know, for almost the whole entire thing. And so that's why I say in theory, you could, once you get to the sensitivity and the instrumentation that you have to do that, you could probe the gravitational environment of 10 to the minus 20 seconds after the Big Bang and see how gravity and quantum mechanics behave together. That's an actual experimental probe that you can eventually get to one day. So yes.
Isn't that one of the big questions of science right now, trying to find is that the unified theory, the quantum mechanics and gravity?
Well, if you want to get kind of technical, your grand unified theories are any theory that includes electromagnetism, the weak force, and the strong force. If you're including gravity, that's considered by definition a theory of everything. So a TOE is including gravity. And at this point, we're pretty confident at our what's known as electroweak unification. So electromagnetism and the weak force can be explained very well in one coherent theory. And we do have a theory that includes the strong force, but it makes predictions that we have not seen yet. Gravity is just this odd child that's like, how do we, like, it's not even really a force. How do we fit it in?
Yeah. So it wasn't the theory of everything then, but it was, I guess that's just another gap in science right now, the unification of quantum mechanics and gravity, or general relativity, special.
Yeah. Well,
one of those.
There's actually a couple of unifications that need to happen. There's explaining all the forces, and then there's also explaining quantum mechanics and GR, because like those are actually two separate problems. So like a unified force, explaining that, and then also essentially having a theory that has quantum mechanics and GR consistent in the same situation. Like quantum mechanics is perfectly fine to explain wherever quantum mechanics is needed, and GR is perfectly fine to explain everywhere GR is needed. But the two situations we know of where they both need to agree produces nonsensical answers. What happens inside of a black hole and what happened at the beginning of time. In both of those cases, when you ask the question, what are the conditions there, you get infinities. Like the theory spits back infinity in protest, which means that there's an incomplete, we lack a key piece of information. Some underlying assumption or perspective is not fully there in order to allow us to make, like to take a step back from both of these theories and say, oh, there's actually a bigger framework, a more simplified model that explains both of those together. So that's an outstanding problem, yes.
So the myth, just to get all the parts, to go back to the black hole conversation. So when you said the inside of a black hole, that's the singularity, right? Is the singularity the middle of a black hole? If
do you want to answer these, or do you want me to keep yapping, or do you? What is the singular? Like, what is a singularity? Like, what is, or is that the same thing as the center of a black hole? Like, what do those things mean? Some heavy questions.
I mean, I consider it like the center of a black hole, but I think it's also where like everything, I don't want to say disappears, but like disappears into, at least, and I would just call it death. If I had one word.
I'm imagining like a diagram. It's like black hole, and at the center, it's like death. I mean, a singularity is anywhere. I mean, you can get really complicated with it. You could think of it as simply as a point, but the point has unknown behavior, or what I would call divergent behavior, meaning the solution explodes. And here's an example of what I mean by that. Like, there's actually a singularity on Earth. There's essentially two. And I know we've talked about this before. When you go to the top of the Earth, the North Pole, and then you ask the question, what is your azimuthal angle? It doesn't matter because you're at one point, right? It isn't until you move away from that, you're diverging away from a single point. But when you're at that point, you could assign any angle and it would still represent where you're standing. It's not until you leave that. So there, but that's a singularity, an artifact of the coordinate system. And it turns out that the black holes have many singularities, but all of them are actually products of the way you're describing them mathematically. You can get rid of those as coordinate artifacts, but no matter what, there's one singularity that is not a coordinate artifact. It's a physical singularity. And that means basically the best explanation we have is what happens when you're there, we don't know. Because the theory, both quantum mechanics says you have infinite energy, and quantum mechanics will say you have infinite energy there, or at least Planck scale energy if you put a limit on it, which we don't understand. And general relativity says you have infinite curvature, which is what does that even mean? So both theories give you a divergent wild answer that means nothing. And the same thing, by the way, happens at the beginning of time. The Big Bang, when you ask what happened at the Big Bang, we don't know. What happened
Everything.
right after? Yeah. Actually, that's
all of it. I mean, that's what you're saying. No, if it's infinite energy, quantum mechanics is the realm of like possibilities, potential outcomes, whatever you want to call it. But that's basically saying like every possible thing. No?
It goes in tune with, remember our conversation with Moises a while back where we were like, where did the Big Bang happen? It happened everywhere because it was
there.
everything.
There.
It was the whole thing was a Big Bang. So
yeah, I still kind of wrap my head around that, but
nobody can.
Yeah. I think inside a black hole, you will find Matthew McConaughey searching for his daughter. No.
Either that or Yoshi's. I think that's where all the Yoshis are. I'll tell you a poetic interpretation. Well, it's actually more mathematical, but it sounds poetic to me. It was told to me by Dr. Romano. He was like, when you pass the event horizon, you can no longer think of the singularity as a place you're going. It becomes in your inevitable future. And that's because when you go from outside of the event horizon and you cross into it, your space and time coordinates interchange with each other. So your space becomes time becomes space. And that doesn't make any sense, but you have to think of it as you have a singularity in the center of the black hole. When you're outside of the black hole, you interpret the singularity as a position. And when you're in the black hole, that singularity becomes reinterpreted to you as an inevitable future. And it becomes all possible paths in your time curve end up in that singularity when you're inside the event horizon. It becomes your inevitable future. And that's very hard to wrap your mind around, but that's another way to look at a singularity. Outside of a black hole versus inside of a black hole. It's different. So
then what's the event horizon?
The event horizon is defined as where that change in your coordinates occurs. It's the boundary where no information can pass. So like an event horizon is a horizon of events. And I know that sounds like I'm just reflavoring the words, but it should offer a little intuition here. When you pass that horizon, people who were trying to check on you could no longer ever know what happens to you. It's impossible. And vice versa, by the way. So that event horizon is literally a horizon, just like when you look at the Earth horizon, you don't know what's around the curve. The event horizon is where that curvature exceeds the escape velocity of a photon. And since nothing can travel faster than light, nothing could ever leave. No information could leave.
That's a good way to put it, with the Earth. The Earth's horizon. I think I've never heard it that way. It's a really good explanation. I love that answer. It's like I thought of answering like, what's a gravitational wave? It's a wave of gravity.
A gravity wave is
What'd you say?
I was like, a gravity wave is from an earthquake. But a
Thank you.
gravitational wave.
I was about to show the meme that actually, so we hear this in popular literature. I'm so glad Brina said this. I'm like ecstatic, to be honest. Like I'm because I like this is really frustrating. I'm sure it's frustrating in the gravitational wave community. Gravitational waves are not the same as gravity waves. Those are separate things. So it's incorrect to say that black holes produce, well, they could produce gravity waves, but what we detected was not gravity waves, they're gravitational waves. Actually.
Yes. So let me go ahead and ask the question that I had brought up earlier. I didn't have it written down. I don't know why I'm getting my notebook.
You want me to read it?
So yeah, sure.
If you don't have it in front of you, so it's from Alex Zamora, right? Who is going to be a future podcast episode guest.
Yes, definitely.
So Alex asks, I'm definitely going to ask Frida this first. Is since black holes bend light due to their immense gravity, and we also know that gravity affects objects with mass, does that mean that light has some sort of mass-like property in order for it to be affected by black holes?
Okay, you can correct me if I'm wrong, but
you're right. Come on.
Since we know like light has two different ways it acts, so it can act as like a photon or a wave. I believe the photon version does not have mass. I think, right? I think that's
you're correct. Right. You're correct.
Mass, or it does not have mass, but the wave version. So like a photon cannot carry energy, but a wave can. So a wave can carry some sort of energy. Like, am I missing?
No, I know what you're saying. I know exactly what you're saying.
I mean, I don't know if you want to take this. I don't want to mess this up. It's such an important question.
Okay, yeah, it is. It's actually a great question. This is what, and these types of things, it's like you have to go into your GR special relativity knowledge and then come back out with a distilled version that makes sense still to explain. And that's not an easy task, but.
Or it's like a black hole. Once you go in, just nothing. One or the other.
Cue black hole jokes. So photons can carry energy. They carry a quanta of energy, right? So E equals h nu, and the higher the frequency, so like blue photons versus red photons, like blue light versus red light, blue photons carry a little bit more energy than red, just because they have a higher frequency. But that's like kind of a quantum mechanical interpretation. If you look at this just from a GR perspective, the first part of the question is actually not exactly correct, and here I'll say why. Since black holes bend light due to immense gravity, black holes do not bend light. What they do is they distort space-time. Photons travel in straight lines, and they travel in the shortest distance possible. So when an object with mass causes a distortion of space-time, a photon just responds by following that distorted path. To the photon, it still feels like it's traveling. So photons like to go to infinity. They're actually pretty much the only objects that like to travel to infinity, and they do it as quickly as they can because they have no mass. And in special relativity, we see that photons travel, they follow the shortest path known as a geodesic. Geodesic you could think of as a straight line on a flat surface, but if you were to bend the surface and say go from point A to point B, there's multiple paths you can take along that curved surface, but one of them is the shortest and least energy intensive. And photons simply follow that principle. Gravity, you shouldn't really think of it as a force. You should think of it as a distortion of geometry. The photon just responds to that distortion. So like photons will skirt the black hole and keep on going. They might fall in and then they're never going to come out. Well, okay, maybe they will, but basically a simple way to answer the question is, does light have some sort of mass-like property? It does in a sense. It has energy, And we do know that energy and mass are equivalent, but we know that the photon has no rest mass. It only can move. And so if you look, E equals mc squared is actually a shortened version of the full equation. It's E equals mc squared squared plus p squared c squared, I believe. And since m is 0 for a photon, E squared equals p squared c squared, take the square root of both sides, E equals pc. So a photon has an effective momentum moving at the speed of light, but it does not have a rest mass. So it has something analogous to mass, but it's not massive at all. And it only responds to the distortion of space-time. So
to us, it definitely looks bent, but you're saying that it's, in reality, it's not bent.
No, well, so you have to kind of think of what is it, like almost do the Einsteinian approach. What does a photon experience? And that's a very hard question, but a photon.
Would it be like a good comparison to say, like if you stick a pencil inside a fish tank and you see the pencil split, like it's obviously not really split, but the reflection makes it look like it is. Is that kind of?
It's not like refraction. It's not an apparent change. It's a change in your coordinate. This is why like even gravitational waves, saying gravitational waves are metric perturbations. What does that even mean? That means if I'm standing next to you, like if Brina and I are standing kind of like next to each other, and a gravitational wave passes between us, kind of like this, right? So we're facing each other and a gravitational wave passes between us. Her and I are going to see, like in an exaggerated sense, her and I are going to see each other get closer, farther, closer, farther, closer and farther. And you would say, are we actually getting closer to each other? Depends on what you mean by closer, because it looks like we're getting closer to each other. But then you would ask the question, what would a ruler look like in between us? And the ruler will also change in size.
Oh.
So that distance looks like it changes, but the actual scale factor is preserved. This is exactly analogous to the expansion of the universe, by the way. Do we say the distances between objects are getting bigger? Yes, but that's not the same thing as saying the scale is changing. Those are different statements. So because the ruler between galaxies is also getting bigger. So to ask the question, is it actually bending space-time? It is, but a photon is experiencing the shortest path still, no matter what type of curvature is involved. That's the point here. It's not, the photon's not being affected by gravity directly. It's following the distortion that gravity causes. And it's wild, like without going into like, and you know, even saying like what produces gravitational waves, right, is not easy to say, because we say, oh, it's an asymmetrical mass distribution. But without going into tensor analysis and calculus, it's very hard to be precise about these things. So like that's the best I can do to explain it. But the ruler analogy is very insightful, I think, to see that the ruler changes as well. That's very important.
It is. Yeah. That helped me understand in a way that I haven't before. That's cool.
I saw, you had your mind blown face again. It
did blow my mind. So then is it right at all to say that the universe is not expanding? It's just the way that we're measuring it is what it is expanding. The measurement itself is what it's expanding. Is that right?
It depends on what you're measuring, but the short answer is yes, it is expanding. But you have to account for the fact that the scaling doesn't change. So like relative scale stays the same, but it is still, right? Like I'm really trying to be careful because I don't like it when science is popularized at the expense of accuracy. And there's always a trade-off, but I'm really trying to be careful here is that the relative scale does not change. So your R, what we call R, big R, which is, if you take a piece of graph paper, you can kind of look at it as like the cells are all getting bigger, but the ruler's also getting bigger. So like what you're defining as an inch stays an inch, but if you were to look at it on an absolute scale, the inch is getting bigger. But to you, the inch is still the same, even though it's getting bigger in terms of an absolute scale. And it's very hard to talk about absolutes in GR because it's like, the GR says that there's no absolute, the frame of reference situation, like what's expanding relative to what, is very hard to deal with when you talk about GR.
So is it kind of like the opposite of inflation? So weird to compare this to money, but you know, like compare it to like
inflation.
No, well, maybe, I don't know. Maybe that's what I'm trying to wrap my head all around it and still ask a question. So, you know, like with money, like you can say $5 in 1950 is not the same as $5 today. It's much more. So $5 today it's still $5, but today it's more. No, it's less. It's worth less relatively because of inflation. So
you could buy less with more, or you buy less with, yeah. What you said.
Jesus.
Less is more.
So is that like the opposite of the expansion of the universe? Measurements, or I'm mixing questions now. I don't even know.
No. It's hard to answer this without a beer or something, but basically I would say, I don't know, Brina, maybe you could say something about this too, but I would say it's similar only in the very loose sense that there's a weight being attributed to a certain value that changes over time. So like I was going to say it's more closely related to cosmic inflation than it is to, because cosmic inflation is an expansion of space-time. Your scale factor is changing, caused by some other force, but that's closer than like economic. I mean, when you get down to it, economic inflation is calculated as an integral under a supply and demand curve. I think I could be wrong here from my Econ 100, but basically it's kind of an arbitrary thing. It does tell you some stuff, but like it's hard to draw an analogy between the two.
Yeah. That's why I was like, I didn't want to make that comparison, but because yeah, what is money? It's fake. We just made it up.
Yeah, this is going to be in the pause. Like, what is gravitational waves? Describe pi CDC.
See this dollar.
Yeah, what is money? Cosmic money. Actually, I'm drinking something for. This is not an official sponsor, but this is cosmic money right here, right? Starbucks.
Yes.
So
in general.
Yeah. So that's it. But this is a good question because it is like. Also, the fact that black holes, I don't know, black holes are just so exciting because they're mysterious. Brina, have you heard of the no hair theorem of black holes?
Yes, I'm not going to talk about it. Very briefly in GR, and I think I towards the very end, so I'm not like super knowledgeable on it, but if you want to go ahead.
I just wanted, the reason why I was asking was because like I think we're really excited about talking about black holes here, and I always try to understand like why are they so exciting, like what is it about them, and I think it's the fact that they produce the most extreme environment you can imagine. They're in all of these crazy situations, right? Merging black holes and gobbling up stars, etc. But at the same time, again, I had this explained to me very well. Actually, again, by Dr. Romano, he said that another way you could look at no hair theorem is that black holes are the simplest objects we know of in the universe. A single black hole can be described by only 3 numbers, and in reality only 2, because the third number is usually 0. So if you can, how many things would it take to describe a human being? Not even just like an individual, like a human or like a rock. I mean, there's so many different, rocks are even more complicated than we might think, right? But a black hole is entirely, all physical properties can be entirely specified from 3 numbers. And that to me is like, it's almost adds to the intimidation. Like they're these very simple objects. They're these primordial, simple geometrical objects that just cause such fascination and destruction. Like that, and everything will eventually enter one. That's the other thing is in the farthest history in the universe, everything is going to become black holes and photons. So yeah, back to the dark stuff, right? Yeah.
That's the black hole being the darkest.
Yeah. Yeah, exactly. So, and it's just, I mean, it's so cool that we can actually detect them. I know that LIGO, there's this property of all gravitational wave detectors called the horizon distance. And it's a very particular number that tells you, in a very simplified sense, how far you could see black holes. And it's defined as something like the distance to which you could see two certain mass black holes merge at a signal to noise of 8 or higher, something like that. Like I forget exactly. This is Bruce Allen 90s, I think, work. I forget exactly. I'm probably butchering this a lot, but I believe that a LIGO plus, which is like the final culmination of LIGO, right, is its horizon distance will be able to hear every stellar black hole merger in the observable universe. So we're going to have a detector that could hear all merging black holes, at least in the stellar mass range, at one point, the entire universe, which is, to me, that's just mind-blowing. And you're working on it, Brina. Like, you're working on that machine that's doing this, and it's just amazing.
Yeah.
So.
Yeah, I mean, I think you mentioned recently that that you were potentially going to be part of the team that's working on LISA. So how do you feel? I don't know if that's still a secret or no.
Only to those who.
She's like, "What's LISA?" No, I can't talk about that.
No, I mean, it's really cool because I just jumped into LIGO like not even 3 or 2 years ago, and then like this next project's coming right at the peak of LIGO. So it's fun to be at the beginning of a project now instead of towards like the peak or the end of it. And I don't want to say end, but like yeah. So I'm really looking forward to it. You know, LISA won't collect data until like 2040, maybe 2030, not sure. So it's gonna be a few years, but I don't know, like the projects I'm looking towards, I could either do, you know, simulations or data analysis, or even like create hands-on experiments for LISA. So it's cool.
Yeah, I was going to ask if there's anything you could say about it at this point, but it sounds like you have a couple of options, directions you can go at this point.
Yeah. So I have to decide what I want to do soon, but I'm going to get to play with all of them at least at some point and see what I like.
As long as you still give me like the heads up, like, yo, we detected the first like this or something, like send me a little text. No. I won't tweet about it.
We'll be the ones to leak it.
Stars, you heard it here first. No. And so LISA is going to be. Do you know when they're trying to launch it? Roughly.
I mean, I think they were aiming for like the 2030s, but I'm not too sure. I don't know. Like the dates always change, so.
Yeah, and especially with projects such as LISA, like these big frontier, what I call frontier projects, like they've never been done before, and it's very technically. I mean, LIGO itself is like a feat of engineering, right? And it's like put that into space and separate them by like like 1 million kilometers and have them all perfectly oriented with each other. Yeah, to me, it's just I don't that is even harder for me to understand how that would work than on the ground. Yeah,
I would like to meet the people that first present the ideas. Like, that's awesome. Like, yeah, we got LIGO. Look, we got 2 lasers that are 4 kilometers long, and then you got one guy like, but what if it was in space? Like, like with the Hubble, like, yeah, we got all these telescopes that could look at galaxies and other worlds and all this stuff, and we got one guy like, well, what if there was a telescope in space? And now we got Hubble, and I mean all the other space-based telescopes, and yeah, it's just, is there, I feel like I'm trying to ask a question there, but I just overcomplicated it. I know I mean, the whole point of space-based telescopes and observatories are to get rid of all the distortion that happens on Earth, right? With, I mean, I know through optical you have the atmosphere and light pollution and things like that. Is there anything with LISA and gravitational waves that is like a particular interest? Like, yeah, well, I guess there's no birds and refrigerators in space, so that might be an easy question to answer. But is there anything more interesting about that?
He knows.
There is a bird. I will let you know. I don't know. I guess being able to find like the other gravitational wave events that like Richard mentioned that could give us more information on other black holes or other systems we might not know about yet is pretty interesting. Yeah, like you said, like I don't know how these people come up with these ideas. I know like one time I think it was a paper I had read, but someone like proposed a detector on the moon.
Yep.
And I think that wouldn't work out because like it was something with like, yes, it would be like a vacuum, or I don't know what was wrong with it, but it was kind of interesting to see like what people can come up with.
Mm-hmm. Yeah. Actually, I think Victor shared that paper with me. That's the first time I saw that paper. You said that to me a while ago, the Gravitational Wave Observatory on the moon.
It sounded familiar, but I don't remember all the details. But yeah, I do remember reading about that.
I know when it comes to LISA with the noise, I mean, there are types of storms in space, but I think the big things are going to be your micrometeorites, cosmic rays, and pretty much everything due to the sun. Like if you have you have external magnetic fields, or if the sun decides to have a coronal mass ejection, or solar particle bombardment, which is a common occurrence anyway, that these things are going to have to be, you're going to need to have your detectors and your storage, especially your data storage, to be protected by that environment, because you have one burst of solar radiation and suddenly you've erased all of your data, or you've thrown off your you fry all your circuits, and good luck fixing that. So yeah, it's got to be extremely robust. I mean, you're essentially keeping a test mass in perfect equilibrium. Like the entire ship is supposed to be around that mass, and that mass can only be jostled by a gravitational wave. It can't be jostled by anything else. So you need to that's why to me it's like LISA is even harder to imagine, because like you're putting it out there into space where it's getting jostled around by so many different things, and it can only be jostled by gravitational waves. Like, kudos to the LISA team, man. That's
Is it going to be in Earth orbit?
I don't know. I'm gonna be honest.
I think it's trailing the Earth, so it will be in. Oh man, again, science creds here.
Okay.
I think so. Here's the idea, and this I have to explain something here. Is how LIGO are two L's, but they're oriented differently. So like so for the people listening, let's I gotta say this, because like in light, like with light, how you have polarized sunglasses, for instance. It's because light can essentially oscillate up and down, or like this, right? So you have two different degrees of polarization. With gravitational waves, you also have polarization. You can have something that causes, like the analogy I used with Brina, to go in and out, up and down, or like this, 45-degree polarization. So LIGO is oriented differently because they're sensitive to different polarizations. LISA is designed like a triangle, so it's partially sensitive to polarizations, but as it sweeps around the sun, its orientation changes. And so it's going to have, I believe, a time dependence on the sensitivity of polarization. So it's basically a single detector. It's like two LIGOs, and then it's put in orbit around the sun. And so I believe it's sharing the Earth's orbit or something like that. But or maybe it's 1 million kilometers away. I don't remember. I just look at pixels on from a telescope. I'm not.
So you answered that very scientifically, and the basis for it's funny because the reason I asked that was because my follow-up question was going to be, can we see it from her? Like,
Probably not.
The reason I asked that was because my curiosity was if you're going to be able to see Lisa from the Earth. Wouldn't that be so cool? You could see the International Space Station sometimes orbiting Earth. So I just wondered if you could see these lasers.
I hope not. I mean, we're already, astronomers are in trouble with like Starlink, for instance. So I think the less things we can see from the ground, the better at this point. But no, I don't think you'll be able to see it unless you like know where to point, and maybe you could see something like if it reflects some sunlight. But I doubt it. So yeah.
You're just gonna see a big triangle falling into Earth at one point.
Yeah.
You're like, I don't think it's supposed to do that.
I mean, that would be so much cooler. Like, I understand there's a lot of astronomers that are not happy with Starlink because you're taking data and then all of a sudden you just see all these streaks across the data. But I mean, with Lisa, it's like, you can't get mad. It's like, oh, look, it's a laser in space. Cool.
It's going to detect like your white dwarf binaries, for instance, which are low frequency. So they're orbiting slower, but there's a whole population of gravitational waves that we're not sensitive to with LIGO, which Lisa will open up. So like, try to we're drawing analogy with an electromagnetic spectrum. Like, it's all based on wavelength or frequency. Same with gravitational waves in an analogous way. But you need, like, your gamma ray detector is so different than your radio detector, and it does it in a different way, right? Same with gravitational waves. You have ground-based interferometers, which have a certain sensitivity, and they can see your compact binaries, like your black holes and your neutron stars and your supernovae. And then you put it into space, you make the antenna bigger, and suddenly you can see white dwarf binaries. And then when you make your pulsars, like all the pulsars we know in the galaxy, and we time them, that's a galactic size detector. Those can see extremely low frequency events, like your supermassive black holes and your primordial gravitational wave signals from the early universe. But those take a long amount of integration. So for instance, like the International Pulsar Timing Array or Nanograv will have data releases on the order of like 12 years. So they've been timing pulsars for a decade, and then they can look at the timing residuals and see if there's a gravitational wave. It's not like the gravitational wave occurs from a quick binary coalescence and LIGO picks it up. It's more like we have to wait and see the effects of the gravitational wave over a decade or more. So it's a longer project.
Yeah.
So Brina, I guess one last question. This is an important question. Is what are your future plans? And now that you've had all this experience with LIGO, you're about to graduate in May. Where is the future of Brina going at this point?
To sleep. No, I'm playing.
Good answer.
So I am planning on attending grad school. I won't say where yet. I think Victor knows a little bit, maybe, on the final decision, but I have a couple of options on what I want to study and do, where I want to do it, but I am planning on continuing work with LIGO and then possibly Lisa, and then who knows where that will go from there.
Nobel Prize, I'm assuming,
Huh? Oh, no. Yeah, but I had told this to Victor a few days ago, like, most of my life has been impromptu, I would say, or like it just happens and I go with the flow. So I don't really like to plan ahead. I just kind of find opportunities and take them if I want to, which has been really fortunate. But I don't know, we'll see what happens. Yeah, exactly.
Well, that's awesome. Well, I mean, I hope that you continue riding the gravitational wave and coming across all of these. I know you will come across all these opportunities, because like I have this feeling that you're just getting warmed up, and I'm excited to see where the trajectory takes you.
It's scary.
Yeah, you're definitely going to gravitate towards a lot of opportunities in the future.
There it is.
There it is. Let's just cut that out.
No, shout out to gravity jokes. Yes, that's staying for the record. Well, awesome. Well, we were really happy to have you. And this was, honestly, this was like an amazing conversation. Like, this is exactly the textbook example of an episode of Receding Horizons that I've always dreamed of having, is talking about black holes and gravity with people who appreciate it just as much as I do. So yeah.
Yeah, it was great.
Awesome. Well, with that, as usual, and for future recurring episodes, to the ladies and gentlemen, children of Brownsville, Texas, surrounding Texas, the United States, Earth, the solar system, and let's just include the Milky Way, these are Receding Horizons.